Okay, we are finally at the end of this chapter that goes on forever. And what I did here was we took a test on the first 4 videos, and then this we're just going to have a short quiz on at the end. And there's only 2 things we need to learn: horizontal pulleys and Atwood's machines. So a horizontal pulley will always involve a table right here, and then mass 1 always sits on the table. So mass 1 always on the table. Doesn't matter how big or small it is, it's always will be the one on the table. And then mass 2, it'll say something like it's hanging. So the equations that we're going to be using are this one. For mass 1, the tension in the rope is equal to mass 1 times the acceleration. And this one I like to rewrite. And we'll say that the tension is equal to m2g minus m2a. It's easier to understand that way. And by putting those 2 together, here is our equation for acceleration. And the only other piece on here that is kind of helpful to know is that the only reason the system moves, there's no friction, is because of mass 2. So the F net in this system is just the weight of mass 2. The weight of mass 2. And that's what this little paragraph is trying to say. Okay, so with those equations in mind, let's give a problem a try. In this scenario, we have mass 1 on the table, mass 2 is hanging, and we are looking for acceleration. So A is equal to m2g, the weight of mass 2, divided by m1 plus m2. And what this equation is really saying is that acceleration is equal to F net divided by mass. So we're back to F equals ma once again. So plugging in your variables, we should get this for acceleration. And then solving for T, or tension, you have your pick of the 2 equations, and I always go with the easier one that says T equals m1a. So try it with your own numbers and see how it works out. Okay, this is just another problem doing the same thing. The first one, it is asking for the magnitude of the net external force. And that sounds really confusing. It is asking for F net. And that was simply the weight of m2, so m2 times g. Then to find our acceleration, we can use that answer because acceleration is m2g divided by m1 plus m2, and then the tension in the cable is just m1a. So they all tie together. Now that was a frictionless surface. If there is friction, it doesn't change it a whole lot. We still have our m2g pulling the block, but friction would be off in this direction. So we're kind of doing a right minus a left. And the way that we're going to figure out the frictional force is we're going to have to find the weight of m1, and that will equal the Fn, the normal for m1. And if we know normal and mu, we can get our Ff. So what will happen is that our A equation will become m2g minus Ff over m1 plus m2. So exactly the same, except we're going to subtract friction on the top. So this problem is the one that we just worked, and I just added something to it. I said, okay, let's let mu be 0.04. So what you're going to need to do is you're going to need to solve for the Fw of m1, and that will also be the Fn. That was 12.92 newtons. Then you will do an Ff equals mu Fn to get our Ff. And then to solve for our A, we'll do m2g minus our Ff over m1 plus m2. All right, here's one that you can try. Just read the problem carefully. It says the 4 kilogram mass is hanging. So when you set up the problem, your 10 will be your m1. And for this one, there is no friction. The next problem will be the exact same setup with friction. Okay, So if you solve the previous problem, set it up again, only this time you're going to need to find the FF. So you're going to have to find the weight of this one, the normal, and then the mu is 0.102. Okay, so that was a horizontal pulley. An Atwood's machine is just simply two masses that are hanging by a rope or a string or some sort of connecting device over a pulley. Nothing is sitting on a table. And if we set this up so that M1 is always lighter, no matter how the picture is drawn, redraw it, and M2 is always the heavier, the set of equations I give you will always work. Okay, the two equations we're going to work with is for M1, it's going to be W1 plus M1A. It is moving up, so we get to have the positive sign right there. For M2, M1 over here, M2, the one that's heavier, will be W2 minus M2A because it's heading down. And because there's one string, tension 1 will equal tension 2. So the tension in the ropes is the exact same. So since the tensions are the same, we'll set these two equations equal to each other. So W1 plus M1A equals W2 minus M2A. And if you didn't want to use W1, it could be MG1. It means the exact same thing. So you'll set those up. We have solve for A by substituting in your numbers. And then after you have A, solve for T. And you can pick either one of these equations. I usually pick the one with the plus because in my mind it's easier, but they will both come out exactly the same. Here's just another problem for you to try. You have to read through, decide which one is M1. Let it be the 12 because that's lighter. 16 will be M2. And then solve for acceleration and tension. It's the final problem, yay! Okay, this one we're going to do the exact same thing. We have got two masses, 2.8 and 5.2. So we have our 2.8 as our M1 and our 5.2 as our M2. I need you to solve for A. And then we're going to do one more step. We're going to pull out an old equation. We want the VF. It's starting from rest, and it's fallen a distance of 5 meters. And we're going to know our acceleration. So you're going to use your VF squared equation to solve for our final velocity. And that is it, Lizzie. I know it's a lot. See what you can work through over break, and I hope that I get to see you on St. Patty's Day. I hope you're feeling better, kiddo. We miss you.